Hello, NDC London. Good morning, good afternoon, good evening, depending on wherever in the world you're watching. It's just gone 3 o'clock in the UK, and it's time to talk about dependency injection. Just a quick introduction from me before we get going. My name is Steve Collins. I've been programming in one form or another since the early 1980s, but professionally I've been doing it since the early 90s, started with VB3, right the way through to now using .NET 5. As many people on the internet with the same name as me, I go by the alias of Steve Talks Code for both my blog and my Twitter handle. I've got a lot to pack in the next 55 minutes, so I'll be leaving questions until the end of the talk, and you can message me later in Track 3 Slack channel. So with the introductions out the way, let's take a deep dive into dependency injection, and I promise no more pictures of needles herein. As I say, I've got a lot that I want to pack in, so I've had to make a few assumptions about what you already know about dependency injection in .NET Core. First is that most of you are familiar with using a host builder of one flavor or another to go and create a container. Whilst you can also create the container directly from the services collection without a host builder, I'm not going to focus on that too much in this talk. The next assumption is that you're familiar with using a startup class to register your services. You'll be doing that using the configure services method and then pointing the host builder to use your startup class. Next, there are various types of dependency injection supported by many IOC containers. But for now, you just need to be aware that out of the box, the .NET Core container only supports constructor injection. Now, when I say .NET Core in the rest of this talk, I'm also including .NET 5 and beyond in that term, though I will be calling out a couple of .NET 5 and C# 9 specifics later on in the talk. If you're using ASP.NET Core, you do get to take advantage of method parameter injection. As you can see here, all you need to do is add the from services attribute to the parameters you want injected from the container. This means that if you have many actions on your controller that have different dependencies, you can avoid injecting them all into the constructor of your controller. That makes your controllers and your action methods more aligned with the single responsibility principle from Solid. Usually, if you want to go beyond the basic out-the-box experience of the Microsoft container, you need to go looking at using other containers, which I'll cover shortly. As I mentioned, there are other injection types that aren't supported in the Microsoft implementation. These include property injection. This is where a class is a parameterless constructor, so dependencies have to be set via properties once the instance has been created. Once all the properties have been set, you then call a method, typically it's called something like initialize, to go and prepare the object for use. Next, we have the named or key-based injection. This is where you identify the dependency you need by using some key value, typically something like a string or an enum value. Last on the list, we have the automated service registration by convention, which is a bit of a mouthful, but in short, the container scans an assembly and pulls out classes and interfaces to register based on a set of conventions or rules that you specify when you're setting it up. The good news is that whilst it's not supported in the out-of-box container, I'll be showing you some workarounds that you can implement so you don't have to go using another container. But why are those other styles of injection not supported? Well, the Microsoft container is what's known as a conforming container, which is a fancy way of saying that it only supports the lowest common denominator of functionality. But it also acts as an abstraction that other containers can hook into via a common interface. You're probably aware that there are a number of other container frameworks out there that can be used with .NET. And in this slide, I show the ones that are listed on the Microsoft Docs website as having been adapted or extended to work with the iService provider interface. The downside is that if you want to use the functionality that's not directly supported by the Microsoft container, you have to manage your interactions with both containers side by side. This means that you need to know how and who is resolving your dependencies for you. Historically, if you were using .NET Core 2, you would usually wire up one of these containers in the configure services method, somewhere in the startup class, and return an instance in the iService provider. In the example here, I'm using an autofac to register an autofac module and return a new autofac container. This all changed with .NET Core 3, but before I come on to that, let's look at how your typical service registrations work. In this snippet here, we have code that you're likely to be familiar with. In this example, we are just registering some classes with the service collection and giving them different lifetimes. As we've covered, in most applications, you'll be using a host builder that initializes the service collection for you and adds some default services. Once this has been done, it will then call your startup class's configure services method to add the registrations you have specified as shown here. After that, it will then call the build service provider method on the service collection to go and create the container instance based on the service registrations you've given in your method. Once built, the container is then used to resolve instances of services whenever they're required. Now, on the previous slide, I said that when moving from .NET Core 2 to 3, or now .NET 5, we are no longer required to return the service provider. In fact, it's now actively discouraged. If you try and return the service provider from configure services, you'll get a Roslyn Analyzer warning. The reason for this is that since Core 3, the way the service provider is created by the host builder has changed. What this also means is that whilst in ASP.NET Core 2, there was a small performance boost by implementing the iStartup interface when using the web host builder, this is no longer supported in the generic host model. If you want to use an alternative container, there is a use service provider factory extension method that you can call when setting up the host builder, and that gets you the alternative container to resolve instances from your Microsoft abstraction. Whilst that will register the custom container, you still need to go and perform any container-specific configuration with the configure container method. You can do this using the configure container extension method on the host builder, but to be honest, it's a lot easier to do it in the startup class as shown here with an example for AutoFac. Whichever way you choose to do this, you receive a builder instance that is specific to the third-party container and allows you to use that container's own registration methods. So for example here, AutoFac will provide a container builder where you can register its modules. It's important to note though, that as the container is built by the host builder, you cannot access the created container until you get to the configure method, where you access it through the application services property. So having covered how the container gets built, let's give some consideration to the lifetimes of the object instances you want the container to create for you. Now, I'm sure that this is familiar territory, but I've included it to make sure that everyone is up to the same level of understanding before we start delving a bit deeper. Firstly, we have singletons. These are created only once and live for the duration of the container lifetime. Next, we have transients, our fair weather friends that come and go as and when needed. And last but not least, we have scope lifetimes. These stand between the other two, but I'll cover them in more depth a little bit later. The thing to consider with these different lifetimes is that some play well with each other and others really should be kept apart. So let's break it down. Starting with the shortest lived of the lifetimes, the transient can accept objects created with any of the three lifetimes. Moving up through the lifetimes, we next have the scope lifetime, which because it's slightly longer lived than a transient, shouldn't have a transient lifetime object injected into it. Lastly, as the singleton is the longest lived of all, this should only have other singletons injected into it, and not the other two. Now, I try to choose my words carefully when describing these relationships because there's a general misconception that it's not possible to inject incompatible lifetimes into each other. But that's not strictly true. I can't speak for the other containers, but the Microsoft container will not stop you. If you have a singleton and its constructor requires an instance of something that has been registered with a shorter lifetime, transient or scoped, the container will happily give you that instance. The problem is, the instance that you get will have its lifetime promoted up to become the same as that as the receiving instance. In other words, a transient instance will be locked into a singleton and not released until the singleton is disposed of. And that doesn't happen until the container is done and dusted. This is known as a captured dependency, where the transient or scoped instance, like the insect in amber shown here, is imprisoned in an outer shell, which in our case is the singleton. But you may be wanting to hit the pause button and go, hang on, when I've done this before, I've got an exception. Well, yep, that can happen. By default, it only happens when your ASP.NET Core environment variable even is set to development. This is done by some hidden magic that lies in the host builder. However, you can explicitly turn this behavior on by setting the optional validate scopes parameter to true when creating the service provider. But this has a performance hit at startup, so the general guidance is not to do it in production, and that's why the host builder only sets for the development environment. Whilst I haven't got time to cover it here today, there's also a validate on build method that you can use to try and help identify any registration problems at build time, but it's fairly limited in the problems it can identify. So how much it gains you, not really sure. So moving on, Given that singletons live a long time and can be dangerous when mixing with other lifetimes, let's consider why we actually use singletons and the typical use cases. Given singletons can be accessed anywhere within the application, things get a bit tricky if your application uses multiple threads. Therefore, singletons should ideally be stateless, so you avoid threading complications. Sometimes, however, you may well have some sort of state that you need to share. These might be pooled resources, in-memory queues, or some other type where you're in control of a limited resource that multiple things are dependent upon. Factory classes I'll talk about later, but typically these are created once, and then their methods are called to create shorter-lived instances of some other dependency when required. You may have an ambient singleton, which hides the complexity of accessing shorter-lived objects, something like the HTTP context accessor in ASP.NET Core, and that uses async local storage behind the scenes to avoid capture dependency problems. The last of the cases shown here is a mutable state. This is where you don't want to have to recreate a resource object over and over again when you know that the data within it won't change while the application is running. For example, you might have some lookup data that you only want to read once from a slow repository, such as a database, a file, or a network service. If you really must have state, give some thought to letting .NET do some of the heavy lifting for you. If you have collections, consider the concurrent collections namespace, where the thread safety stuff has been already done for you. For read-only properties, make the underlying field read-only, so that if someone comes along later and makes it a read-write property, at least you're forcing them to have to do some work and make them sort of stop and think about, why am I changing this read-only property to a read-write? For those properties that really must be read-write, you should maybe consider using a thread lock. So in this slide, we can see that we're ensuring all property access is managed by the thread lock. That way we can ensure that the value is only changed by one thread at a time. Now, the problem with this approach is that by serializing the access of the property, you will be getting a major performance hit as you're forcing everything that touches that property down a narrow one at a time alleyway. And you end up with threads queuing, or even worse, you may have a thread deadlock. So you may want to give some consideration to your design and maybe give some thought as to whether you need to use a thread lock or maybe use async local. I don't have a panacea for this, but I'm just warning that if you've got that in your design and say a very multi-threaded application, you may want to go back and look at your design because it's very much a code smell. Lastly, consider the impact of having disposables in a singleton. The problem here is that if you expose the dispose method and a consumer calls it, everything else has lost access to the disposed resource, which can cause an object disposed exception to be raised elsewhere in the application. However, you do still need to make sure the dispose method is there for the container to clean up after itself when it's done with the resource. To get around this, maybe you should consider abstracting the class with an interface that exposes all the members except the dispose method. That way, if the interface is registered as a service and not the concrete class, when the instance is served up from the container, you've put some guardrails in place that make it difficult for a consumer to accidentally call the dispose on the instance. That doesn't stop someone who wants to vandalize it and go and cast it into the right type and call dispose, but there you go. For transients, there's not really a lot to say, other than just be careful about doing a lot of work in the constructor. The reason for this is you don't have control over when the instance is being created by the container. This could have a major performance hit on your application if they're doing lots of work getting data from a database, say, each time they're created, and there's lots of them being created. If your transient must go off and do some database work, maybe do it through an explicit method call rather than in the constructor. Moving on to scope lifetimes. These need to be approached with caution and handled with care. In fact, I've seen various blog posts and tweets where people have said that they abandon them from use on their projects. Now, I think that is a little bit drastic, but I understand the reticence, as they can come back and bite you when you least expect it if used incorrectly. So hopefully I can try and clear up some of the pain points. We've already covered how scoped instances should be used with other lifetimes, but what exactly is a scope lifetime? Commonly, you'll get a quoted answer that they are created by ASP.NET Core for an HTTP request response lifetime. But that's not really the whole story. Whilst that is a common use case, a scope is not tied to ASP. You can go and create your own scopes. But that still doesn't answer what a scope is. As far as I'm concerned, a scope is really there to ensure that objects created and resolved are within a single unit of work and that they're consistent. So say you have several classes that all interact with each other and all depend on receiving, say, an iWidget instance in their constructor. You want to make sure that they all receive the same instance from the container rather than a transient, which will give you a new instance every time you want it. So in that respect, a scope lifetime is a bit like a singleton in that you get the same instance that can be shared. However, outside that unit of work boundary, you expect to get a different instance. So in that way, it's a bit like a transient. So to come back to the common use case of a web request, if both Bill and Ted go and make a web request, those request response pipelines are individual units of work and are separated from each other. Therefore, the scoped instances that get resolved for each of those pipeline requests are confined to each request response pipeline, and they don't see each other. So they're very much like transients in that way. Away from the web, you might be writing, say, a Xamarin app or a console app, and you may want to manually go and create a scope yourself. This can be done by calling the create scope method on the iService provider instance. This gives you back an iService scope with a single property of service provider, which in turn is an instance of iService provider again. But this time you've created a boundary that can serve up scope services. That's a bit of a mouthful to explain, so maybe looking at how ASP.NET Core does it will provide some clarity. As I say, in ASP.NET Core, the creation of scopes is taken care of for you when a request response lifetime is started. The server will create a load of service features, but the one we're interested in is the request service feature. As I described just now, the scope factory is used to create the scope as highlighted here. That scope is then used to create the scope service provider, which is then accessed from HTTP's contexts request services property. As someone writing an ASP.NET controller, all of this is hidden away from you. You don't really care. All you care about is specifying your dependencies in the constructor or the action method of your controller or endpoint. However, there is one area in ASP.NET Core where it's worth knowing what's going on under the hood, and that's middleware. When we talk about middleware, we think about intercepting and handling HTTP requests and responses. Now, because you might assume that middleware is a scope, because of that, you might assume that the middleware is a scope registration, but that's not strictly true, because there's two different ways of writing middleware. The one that most people are familiar with is convention-based middleware, as shown here. With this type of middleware, you accept a request delegate in the constructor and then call it from within the invoke async method to move to the next middleware in the pipeline. Either before or after the delegate call is where you may go off and do your own work. For example, you may go off and do some logging. In some cases, you might be writing a terminating middleware, where you generate the response and you don't call the delegate next down the chain because you're handling it. The only time you might pass it on is if you can't handle it. That's something like the static file middleware works. If you have dependencies other than HTTP context, you can add those as parameters to the invoke async method, and they magically appear when the method is called by the pipeline. But how does this all happen? When you register middleware, it is done in the configure method of the startup class. At this point, the container is already baked, so you're not adding the middleware to the container. That's a sealed unit. You can't go and mess about with it anymore. Instead, what you're doing is inserting a delegate into the invoke async method. A delegate to the invoke async method, and that will be doing the actual work in the pipeline. To do that, a single instance of the middleware class is created by the useMiddleware method. When that single instance is created, any dependencies are resolved from the root container. That's where the container stores your singletons and your transients. Now, as we saw earlier, if the constructor is only called once, when you request a transient or scope dependency into the constructor, it'll become a captured dependency. What you also need to bear in mind is that the pipeline is created before the first request. So you won't be able to access anything related to HTTP context in the constructor of your middleware, as it doesn't exist at that point. You're still building the pipeline as you're going. If you do try that, you'll get an invalid operation exception, because at that point, the HTTP context doesn't exist, so nothing can resolve it, and kaboom, it blows up in your face. Other scope dependencies that are not part of the pipeline may well resolve, but as I say, they may become a captured dependency. So how does the request in that scope that is scoped get dealt with? Well, as the request moves through each layer of middleware in the pipeline, the invoke async method gets called through the delegate chain, not through some interface or abstract contract. To do this, when the middleware is added to the pipeline, the request delegate is created. The delegate acts as a wrapper over your invoke async method. So as you can see here, the request delegate is passed as a parameter to the middleware constructor to enable the request to be passed down to the next one in the chain. You're free to go and add any scoped and transient dependencies parameters to the invoke async method if you need them to do some work. So rather than the constructor, by doing it in the invoke async, that's being called through by the middleware, and you've got a scope at that point, so it can resolve them. In the previous example, I demonstrated how dependency injection works with the convention-based middleware. But what's less well known is that there's also an interface way of doing middleware. The interface is iMiddleware. That interface has just one method, invoke async, which has the context and request delegate passed in as parameters. As this is a fixed signature of the interface, you can't add your scope parameters here, so you have to go back and do it in the constructor. Now I say don't do that for a convention, but what's happening is that it works in the opposite way round to convention based, because what you do is you go and register your new middleware with the container, and behind the scenes the used middleware will go and look at the container if it detects an iMiddleware and get the container to create it, rather than do it all through reflection as it does with convention based. Now I mentioned being careful with disposables earlier, but I'd want to dig into it a little bit deeper with some edge cases. Earlier, I said you should hide the dispose method from consumers, as the container will take care of disposing your singleton or your transient or scoped when it's finished with it. The last bit of the statement is true in most cases. But as you can see here, there are a couple of extension methods for creating singletons where you go and create the instance yourself. The container's not newing it up, you're newing it up. And the container won't dispose of those for you because it hasn't created them. If you do create an instance of a disposable class in this way, there's a bit of a problem. Namely that out the box, there's no obvious re-entry point back into your class to get to the configure services method or the startup class itself to get a reference to the instance to then go and dispose it. So why would you take that approach? The reason you may be creating an object in startup is to pass arguments to the constructor where the parameters cannot be created by the container. That you may have some third party thing that needs something special that you just cannot create from your container. If that is the case, you should maybe consider using a factory, which I'll talk about in a little bit. If you've got no other way of really getting around this and you really must create your instance inside your startup, you do have one last get out of jail card. Behind the scenes, there's an interface that is automatically registered by the host builder called iHost Application Lifetime. This can be injected into the configure method by adding it to the parameter list. Here you can register a handler for the application shutdown, which is past the object that you want to dispose of. That's fine if you've just got one object, because you specify it within that application shutdown method. And a bit like evoke async, you can add as many as you want. But it does get messy if you've got lots of them. So what I would say is if you've got maybe sort of 4 or 5 different disposables that need to be done in this way, you might want to create one wrapping disposable class that then presents those class instances for you and then goes and disposes of them, just taking that in through the parameter. Coming back to hiding the dispose method. If you cannot change the class as you don't own the source code, and it doesn't already have some abstraction that hides the dispose method, you may want to consider some of the gang of 4 patterns, such as facade, adapter, bridge, or proxy. These are all variations of a theme where you create some kind of wrapper class that encapsulates your thing that you need to dispose. The last point I want to make is a rare one, and a code smell. But if you have a class that is what's known as a control freak, and insists on disposing instances passed into it, then instead of getting the container to create those instances, maybe consider using a factory and the patterns I've just mentioned. Next, we have some gotchas that can come up and bite you when registering or consuming services from the container. Consider what happens when the same service type gets registered multiple times against multiple implementations. Now, you may well be doing this deliberately because you have several implementations that you want to iterate through. These might be set of validation rules, for example, or maybe a collection of processing types that form an enrichment pipeline that you chain together using the visitor pattern. But it can happen by accident. For example, you may have a Git source code merge that's gone wrong, where you had one old registration and you've got a new registration, and it's merged and gone wrong, and both of them suddenly appear. You may be using extension methods, and behind the scenes, without you knowing about it, that's going off and registering a different implementation to the same interface or service that you're registering, and you don't know about it. Whatever the reason, there can be unintended consequences because of the way the container works. Namely, it works on a last in wins principle. So if you use an extension method after your registration, it'll be the extension method's implementation that'll be the one that gets resolved by the container. So you need to give some thought as to the order in which you set up your dependencies and configure services. So you may want to go and call extension methods first before your services. Of course, if you're writing an extension method, especially if you're publishing it onto a wider audience on, say, NuGet, the onus is on you to play nicely. As we know, there needs to be care around lifetimes, and things get messy if there are multiple registrations with different lifetimes. So you may think you have registered a singleton, but something comes along and trumps it with a transient or scope registration. Now, it may be that, as I mentioned just now, you deliberately want multiple implementations. But if we do want to avoid that happening accidentally, registering the same service multiple times, there are two ways out the box to do this. The first is to use the variations of triad methods, where the first registration is kept and subsequent registrations are ignored. So effectively, we're telling the container to flip its concept of last in wins principle on its head, and now the first in wins principle wins. Once you've got something in there, no one else can come and override it. The second approach is to use the triad enumerable methods, where both the service type and the implementation type are taken into account. So in the examples here, the triad singleton will result in just one registration, even though it's been called 6 times. But the triad enumerable will result in 3 registrations, as the implementation type is also taken into account. So that's some of the gotchas. Let's try and come up with some helpful hints and tricks now. If we flip what I've just talked about on its head, and you deliberately do want to register multiple implementations, the callers that need to iterate over it, they need to know about it. How does the consumer know that you've got multiple implementations? So the way to do it is they have to explicitly request the IEnumerable of the service type to get all those implementations. If you don't do this, the instance you receive will either be the last or the first implementation registered with the container, depending on whether you use triad or not. If the order of the enumerable is important, there needs to be a way of differentiating each instance. Without that, the consumer will have to rely on the order that the registrations were performed. There are lots of ways of handling that. One is to create a comparer that implements the iComparable interface for your service type. That can then be used with an order by in link that receives the enumerable, so you could do that inside your controller. You could create a dedicated class that implements IEnumerable, and the caller requests an instance of that. But for that to work, you will need to inject the IEnumerables of the service type into it, and then have some ordering logic in there, and then you have to register your class so that the consumer can then go and request your class from the container. So it still adding yet more boilerplate. Lastly, you could just write a Lambda expression for IEnumerable inside your container registration. That then serves up instances in the required order. Going the other way round, you may have a single class that's got multiple interfaces, especially if you've gone down the interface segregation principle route from Solid. If you register the type of each interface individually, each registration creates a distinct instance, when really what you probably want is the same instance returned just through different interfaces, especially if it's a singleton or scoped. If you want to access the same instance through those different interfaces, you should register the instance first by its actual concrete class type. Then, what you can also do is you can use in Lambda expressions using the getRequiredService method of the iService provider to go and resolve the main instance from the container and return it via the interface, as I've got shown here. In some cases, you may want to aggregate the interfaces together into a composite interface as shown here. This may be a benefit if you don't want consumers to be able to request the concrete implementation directly. If you think back to the iDisposable issue I mentioned earlier, where you don't want the dispose method to be accessible by clients, then you don't want the concrete there because the dispose method will be there. So in the example here, I've registered my implementation using an aggregated interface rather than the disposable concrete class itself. I've then also registered the same singleton instance against the individual interfaces to receive the same instance, but this time calling back into the container to ask for the aggregate instance interface as the service. Next, we have open generics, where you define a type on the class type. Type parameter on the class type. Now, the place you may be familiar with this from a DI perspective is the generic iLoggerT interface, where you may be using it in your controller constructors to get an iLogger instance that's typed to your controller. Similarly, you may be familiar with the iOptions interfaces that get registered when you use the configure method that binds configuration to objects. If you want to register your own generic type, the C# syntax doesn't lend itself to referencing open generics within a generic declaration. The syntax just isn't there. So instead, we have to use a non-generic registration method where we use the type of keyword to get the service and implementation types without giving a closing type parameter. In the case shown here, the iDoSomething generic interface and the doSomething generic interface are shown with the angle brackets, but without a closing type parameter, as this will be supplied by the consumer. Think back to how you call iLogger when you write a constructor on a controller. You ask for iLogger and then you pass the type of your controller. Behind the scenes, the container makes use of the make generic type method on the type class to go and create a closed generic type. So it's just taking your open generic and making the closed generic type. For example, your do something generics would be a do something generic of strings. It then uses the type with a bit of reflection magic to go and create a closed generic instance. That's the thing that's going to get returned back to your controller through the container. If you haven't moved to .NET 5 yet, you may well hit a problem if your type definition includes a constraint on the generic type, such as limiting it to maybe being a class, or the generic has to implement a particular interface. The problem is that with the make generic type in .NET Core 2 and 3 was that if you had a constraint on there, it was throwing an argument exception. Luckily, that's where Jimmy Bogard of Automapper and Mediator fame has come to the rescue. He did a pull request that added a try-catch block around the make generic type, and it swallows that argument exception. Now, this allows constrained generics to be resolved in .NET 5. Great. Except it took him 4 years to get his pull request to be accepted. If you read Jimmy's blog, you get to understand why there's been very little change in the Microsoft container since the first version of .NET Core. In short, you must ensure that all those other container technologies, that implement the iService provider interface don't break, which in turn means that you just can't just go and fix something. You have to go and write a whole load of unit tests that not only show that your change fixes something or brings something new to the container, you have to go and show that your change doesn't break those containers or messes up the way that those containers work. Next, I want to talk about a couple of so-called Gang of Four design patterns that are really relevant in the DI container world. Now, throughout this talk, I've touched on the factory pattern. And you may be thinking, well, Steve, hang on. Surely the whole purpose of a container is to be a factory of instances for me. Why would I have to go and write a factory class? Well, as we've seen, there's a few gotchas and a few deficiencies within the container, so sometimes you have to give it a helping hand. For example, you may have a class where some of the constructor parameters are not known until runtime, as they may be captured from a user input. In those cases, you can't get the container to create the instance for you because, well, the container won't know it because the user hasn't input them yet. Now, there are some workarounds. It's not, it's hideous, but you could do some hack with async local, but that's really nasty stuff. Similarly, you may have an instance that when it gets created, it's such a resource hog, you want to get rid of it really, really quickly. And if you're leaving it to the container to do that, it's kind of a bit like garbage collection. You're not really in control of when it's going to get disposed of, and you don't want something hogging up all the memory or resources on your web server. So in that case, what you want to be able to do is say, I want this thing and I want to be in control of when I dispose it. Lastly, at the start of the talk, I mentioned that the Microsoft container doesn't support property injection. But by using a factory, we can effectively simulate property injection by getting the container to instantiate the class and then set the property values before returning the fully prepared instance. These are just a few cases where the factory pattern comes into its own. So as a very quick and very contrived example, we have a class here that will register as a singleton. Next, we're going to create a class that consumes that singleton, but also requires a name parameter in the constructor. Now, given that the name parameter cannot be known by the container, as it will be provided by the runtime of our API, we can't add it to the configure services. You may notice that I've used an immutable class here, but I could have used a C#9 record. Now we're going to create a factory class. First, we take the singleton and cache it in a field, as shown in the blue highlighted constructor. We then have a creation method that will go and new up our short-lived thing for us, using the cache singleton and the value passed into the method as the name parameter. Next, we add the factory to the configure services as a singleton. And finally, we have our controller that will take our factory and its constructor. Later in the get action, we'll then call the make method to go and create the instance of the short-lived thing. Very contrived, I know, but I wanted to give a flavour of using the factory. And apologies for the small font if you're watching on small screen, but I had a lot I had to pick into that slide. So to summarise factories, usually you will register the factory as a singleton, as most of the time you want it to be stateless. The variations are the parameters in the create method. As it's a singleton, the only other dependencies that should be injected into it are the other singletons. If you need transients or scope dependencies, you could take the iService provider itself as a constructor parameter, but proceed with caution. Direct use of the iService provider is considered a version of the service locator antipattern. The reason it's an antipattern is that you're becoming a tight coupling to the container interfaces, which in most cases you don't really want to do. You want your classes to be completely oblivious to the container. You just want to say, I want this dependency. However, the factory pattern classes fall into a group that I refer to as servicing classes. These are plugging the gaps in the container functionality that are effectively an extension to the container. So with this in mind, I think as long as the factory classes are seen in that context, and you don't go referencing iService provider wholesale through your application, your domain stuff, I'm fairly relaxed about doing this because it's being pragmatic rather than dogmatic. If you're worried about factory classes exposing that anti-pattern and the tight coupling, you could always create an abstract interface that make that class private inside your startup class. So that way you only get to see the factory create methods, not how you've gone and created that factory. Variation of the factory pattern is the builder pattern, where rather than prescribing which dependencies are needed up front and creating the instance immediately, the builder is much more flexible. The way I like to think of it is like ordering drinks in a fast food restaurant. In some places, the factory is like the person asking the person for a cola, where they've got a standardized dispenser with a fixed set of options and they just make you a standard drink. With the builder, it's much more like the modern dispensers that you find in these places, where you can say, well, I've got a base cola and I want to add a dash of lime and a dash of vanilla and a dash of cherry, gradually composing it up as you go along until you've got your finished drink. So with the builder, we start off much like the factory by registering it with the container. However, this time we register it as a transient because you're going to be mutating the state of the builder once it's been created. In its constructor, we take in other dependencies from the container. Consuming classes take the builder as a constructor parameter and then start using the methods and properties to build up the new instance to be constructed. Then once we have we've configured our builder with everything that we want, we can go and call the build method to go and create our instance. Now, you're probably familiar with the builder method from the web host builder and the iHost builder that you use in your main to go and create your host. Typically, the resulting instance will be immutable. The last thing to mention is that, like the factory, if the instance you create out of the builder is disposable, it's the caller that's just asked for it to be created that needs to be responsible for disposing it. So it needs to wrap it with a try catch finally or the using syntax. It's not the container's responsibility. So in this final section, I want to talk about plugging in some of the gaps in functionality that the Microsoft container is missing. I mentioned earlier that property injection is not supported out of the box by the Microsoft container, but you can get around that by using the factory or builder to create the instance and set the properties before returning the instance from a create or build. Another place where this can be useful is if you need to create instances of struct values, where some of the properties come from the container. Now, the problem here is that you simply cannot register a value type with the Microsoft DI container. It's just not supported. So you need to go and get all your dependencies and instantiate the value type it yourself. So here you see I'm attempted to try and add a struct type registration using the generic add transient. And here's the Roslyn analyzer error to tell me that that's a no can do. You could think, aha, maybe it's just because I'm using the generic registration. I'll try and use the non-generic version. Yeah, nice try, but you don't get the compile time error, but all you've done is kick the problem down the road to become a runtime error. So how do we get around this? We simply create a root factory or builder that takes in all the parameters we need to populate the value types. Now, the example here is very contrived and offers no benefit of just creating the object in your own code. However, if some of the properties that need to be taken from the container, this is where the factory can grab them in the constructor or via an IO service provider and then put them together with the method parameters. Which leads us from value types to C#9 record types. Now, I won't go into a lot of detail here as I'm it's 3:45 and I'm running short of time. But basically, there are reference types that behave like value types. And as they're reference types, you can register them with the container. However, given that record types are mainly there for entities, you're more likely to use the factory pattern for the same reasons as I've said before. You're very unlikely to go and create records out of the container. If you're interested in finding out more, I do have a blog post that shows how to write a record factory. And that's a lot of the ideas that I've just explained in the last few slides are in there. Next, we have something that no one really talks about in dependency injection with C#. It's our little secret. We nearly always talk about classes and interfaces being registered with the container, but delegates are also first-class citizens, and you can also register them. Now, in theory, you can register the anonymous delegates from the funct family, but these are hard to distinguish from each other because they're just generic function signatures. So instead, we go old school, right back to C#1, to something that doesn't get much attention, and that's custom delegates. Now, I'll go into details on my blog, but to give you a quick example, I really hate system date time now property with a passion, because it's non-deterministic, and by its very nature of being real time, you just can't unit test it. But what we can do is to create a delegate function that will call the system date time now property on our behalf. The signature of our delegate in this case is a function with no input parameters, and it just returns a value of date time now. By creating the delegate, we're creating an abstraction without all the ceremony of first go and create an interface and then go and create a class and implement that class and have that class then wrap that dreadful static now property. This makes your registration code much cleaner, as you don't need all that plumbing work. It also feeds into the single responsibility principle, as the delegate just does one thing. If you have multiple datetime related functions, you may still want to use an interface and class, but if those functions don't share any logic, you could just go and create multiple delegates. This is where the custom delegates have the advantage over the funct family, as the delegates can all have their same signature, but they're distinguished by the delegate name. If you try and do this with the funct family, They may all have the same function signature, and then you fall into the trap of multiple registrations that all look and smell the same. So you'd only get the last one unless you ask for an IEnumerable, and then how do you know which of your enumerable ones is the one you want? So using a custom delegate from a unit testing point of view, the delegates are very easy to mock and create your own implementations, as they're just function definitions. So in this case, the function just returns a date time, which for a unit test you can set to a fixed value, and you can compare your fixed value in your assert statements. Now you may notice I've registered the delegate as a singleton, and may be thinking, well, hang on, that date time that gets returned will be captured the first time it called. But that's not the case, as we're capturing the delegate, not the delegate's results. We're just sort of saying, I've got this object that represents a function, not the function result. You don't get the result until you actually invoke that delegate. And this is the same principle that we saw when we were talking about registering middleware and having a delegate that wraps the invoke async method. So in this very contrived example, I consume the delegate in the controller constructor and cache it in a field. I then invoke it at the time the constructor is run and cache that result in a field. So that's the first time I've invoked it. In the get action, I force a 3-second delay, and then I call the delegate again. I then take the return string of both values. As you can see, the results show that even though the delegate is a singleton, the result is not generated until invoked. The first invocation is in the constructor of my controller. The second is in the method, hence the 3-second difference shown in the result. This is the same principle I described earlier about how middleware pipelining works. A feature that is supported by other containers, such as AutoFag, is being able to specify a dependency to be resolved by the container using a string name or key. Now, it's considered a bit of an anti-pattern because it comes back to the idea of your application code shouldn't know about the container's mechanics. But what if you could get your container to do it with the class having no knowledge of the container whatsoever? So this occurred to me a while ago when I had a situation where the type of a mapping algorithm to use was determined at runtime by the value being returned from a database. And rather than have some hard-coded switch statement inside my repository that would need to be updated each time a new value came along into the database, I wanted something that could be injected from the container just to give me the mapping functionality I need. Now, it's a bit long-winded to describe here, especially as I've only got 10 minutes left. So there's a link to my blog post, but to give you an idea of what's involved, I do have an example. First off, we create a common interface with some classes. So here we have a temperature converter that takes different scales of centigrade, Fahrenheit, Rankine, and Kelvin, and converts them to kelvins. So Kelvin will be a 1-to-1, and you've got the different formula. And I haven't looked at those formulas for many, many years now. We will then register them all with the container as their actual types. Following on from what I was saying about using delegates, we also have a delegate declared that takes a string as its input parameter and then returns the required implementation of the iKelvin mapper interface. Now in the code here, I've got a simple switch statement based on character values, but I could have done something a bit more advanced and more flexible using dictionaries or possibly custom attributes, or maybe sort of using pattern matching with C#9. Whichever way you choose it, the delegate is the secret source in which allows us to lift the logic out of the consumer and up into the container. The consumer will use the delegate to pass the string in and get back the correct mapper instance that it needs. In other words, we have something along the lines of an abstract factory pattern. So now we've got our consumer, the class that's called getTemperatures. That has a method that takes a scale as a string and a decimal value of that you want to go and convert into kelvins. Our class has no knowledge of the container's iService provider at this point, or how the required implementation will get chosen based on our string. It just knows that it can pass the delegate a string, and it will go and get a converter that will return it back in the scale as specified by the string. The decorator is another gang of 4 pattern that can be used to extend the functionality of the class. It does this by wrapping and then re-implementing all the members, but where necessary, intercepting the incoming parameters and outgoing results to do something else. Now, a common example of where you're likely to do this is if you've got maybe, say, something that logs what's come in and logs what's gone out. Now, you may have that on every method call. You may choose to have it just on some of them. That's your prerogative, and that's what your decorator does. You're not baking it in. You're not having to do anything special to your original class. To do this, when you write your decorating class, you need to have the original class injected into the decorating class along with any other dependencies, which in our case is going to be a logger. So in this example, we have a class called doSomething that implements the IDoSomething interface. First, we register the class as a concrete type and not through its interface. We then have a decorating class called logging doSomething, and that takes the original doSomething class and also requests an instance of iLogger. It then re-implements the getHello message method, this time with code that intercepts the input and output of doSomething's version and writes those out to the log. We then go back and register the new logging doSomething against the IDoSomething interface, which is used by consumers. And you'll notice there that in the original one, I haven't used the interface. That's to avoid the IEnumerable problem. The last missing feature from the Microsoft container that is supported by others is registration of services by convention and assembly scanning. Now, I'm not personally a big fan of doing that, as I'm a bit of a control freak, and I like to know exactly what's going on. As we saw earlier, it's possible for registrations to stamp all over each other, depending on the order that they're registered. So however, I do get it. If you've got masses of classes to register, and that can be a really laborious task, I totally understand why you may be looking for a shortcut. This is where there's several offerings out there, but probably the most well-known is Scruter, where you can define rules and criteria for registering classes and interfaces. One nice thing I do like in Scruter is the ability to register decorating classes with a much simpler syntax than the hand crank version I showed in the previous slide. My final topic I just want to give a brief mention to is about performance. Some of your registered classes may take a while to be instantiated, which will hit you when an object is created for the first time and may impact on your users. If this is the case, you may want to consider having some sort of background hosted service that goes and starts up with the application, and it goes and requests all the registered services from the container. This has two benefits, namely singletons get instantiated and are ready to go when the first consumer requests them. The second is that the transient and scoped instances benefit from JIT compilation. So even though the instances that you're currently creating with your background service just get thrown away, you're not making use of them. Future instances that get created, they'll get created a little bit faster because the JIT compiler's already done some of the work and it knows how to go and create them. So Andrew Locke has a really good blog post on this, and I highly recommend reading it. So I've got about 5 minutes left. That just about wraps it up from me. Thank you for coming to my talk, and I hope I provided some value, even if it's only just 1 or 2 nuggets of gold that are hidden away in .NET Core. If you want to hear any more of my ramblings, I'm on Twitter quite a bit. I do have a blog where I've written mainly about dependency injection and configuration. Before I go, a few honourable mentions, because I've stood on the shoulders of giants in this talk. It hasn't all come out of my brain. Andrew Locke has a brilliant blog that covers all sorts of .NET Core related things, and he's currently writing the second edition of ASP.NET Core in Action, which is available as an early preview ebook from Manning. The Microsoft Docs pages are well worth a look, especially if you're migrating from .NET Core to .NET 3 or .NET 5. Last but no means least, Mark Seaman's blogs and books are well worth looking at to get a bigger picture of DI patterns and anti-patterns. So he covers all sorts of, and the book I've got there, it goes through each of the different open source ones that are commonly used and then compares them to each other once he's discussed how the anti-patterns and the good patterns and why you shouldn't write your own container and all that. So with that said, and just under 4 minutes left, thank you for coming to the talk.